to start off here, I'm going to introduce you to a new function. It's possible some of you guys who have taken calculus might have seen this function. This is called either, and it can have different names. I notice here that they're calling it the floor and ceiling function. I've also seen this called the least integer function and then greatest integer function. So let me write that. The floor function can be called the least integer function, and the ceiling function can be called the greatest integer function. And it's just like how it sounds. Okay, so here you're being asked, what is the floor and ceiling of 2.31? Okay, and so the least integer function or the floor function is just what is the integer, the closest integer less than or equal to 3.21. And then the ceiling function or greatest integer function is what is the next greatest integer. Okay, so not a hard concept. It's really just learning the symbols and what it means. So, and here's also an important point. What if we want the floor or ceiling function of a number that's already an integer, right? So the floor of 5 is 5 and the ceiling of 5 is 5. So let's look at, here's the formal definition. So what's nice about the video is I don't have to pause as I'm speaking. I can just tell you, pause right now, write this down, unless you've already got, wrote a description from what I said verbally up above. And then the notation for it. If we want the floor function, the notation's on the next page, but I'm going to write it here. It's like this. It's sort of like absolute value, but then the bars hook to the bottom. Okay, so if I asked you to find the floor of 3.7, sorry, that's a 3, it's very messy. The floor of 3.7 is 3. Okay, the ceiling of 3.7, okay, so just like absolute value, but the bars come in at the top, the ceiling would be 4. Okay. Be kind of careful when you have to do a negative. So this would be the integer less than or equal to this would actually be -2. Right? Because we go to the left on the number line when we're doing less than. So be kind of careful when it's a positive or a negative. So here's where they show you the symbols. And then when you graph it, okay, when you graph something like this, it's known as a step function because it looks like steps. Okay, because if we're doing, let's see, this is the floor function. So any x value that's less than 1, right, that would map to 0, right? But then when x is 1, so we know the floor function of 1 is 1, right? So then we have the solid circle here, but then 1.1, 1.2, 1.3, 1.4, 1.5, those all map to 1. And I'm sure you can see then that we are not 1-to-1. First of all, this would fail the horizontal line test, okay, because we have sections that are horizontal lines. And we can also verify that by saying that f of 1 and f of 1.5 both equal 1. However, 1 and 1.5 are not equal. That's the definition. And is this onto, if we looked at this function from, let's say, R to Z, okay, could we get an output of every single integer? Okay, so think about that for a minute. Every single integer, like if I said -10, could you give me something in this function that would output -10? And this is actually really easy because everything maps to itself, right? So I could go like that. I could also, this would map to -10. I also could input -9.9, -9.8, right? All of those would map to 10 on the floor function, -10 on the floor function. Okay, so this function is both, actually, no, not both. It's not, and let me write it this way, not injective, because I want to make sure I keep using those words, which is 1-to-1. So it's not 1-to-1. It is surjective, which is onto. So obviously it's not a bijection, which means it's not invertible. Okay, I can't find an inverse to these functions. And so one of the problems on your homework, I forgot if it was the floor or the ceiling function, but it was like x/2, right? And it was just asking you the floor or ceiling, can't remember which, but of x/2. And it's asking if it's 1-to-1 or onto, and I'm sure I said R to Z. Okay, but it would be the same thing, just because I have the over 2, right? It would not be 1-to-1, but no matter what integer I wanted to pick, I could find an input that would give me that integer. So I'm helping you with one of the problems on the homework. So the next thing we have to talk about is composition of functions, and you've done that before. That was part of Algebra 2, and you probably did it some more in pre-calc. So let's title this section Composition of Functions. And there's two different ways that I can write the notation. So if I wanted to find, say, f of g of 2, I could write it with a little circle, or the other way that I could write it is the double set of parentheses, f of g of 2. And we work these inside out. So we would start with this function. And so what this means is find g of 2. Put 2 into g. And then find f of that answer. Okay, so take the answer you get here and then put it into f. So that would be 4 plus 5, which is 9. Okay, so then we find f of 9. And f of 9 would be 18 minus 3 is 15. Okay, so I can ask you to do that with a number, or I might say to you, find this, g of f of x. Okay, so what that means is take f of x and put that into g. So this becomes like your like quote x that goes into g. Okay, so you have to put the entire function in. So g of f of x means take this and then put this in for x. Okay, so I'm putting this into a function that says whatever my input is, square it and add 5 to it. Okay, so my input is 2x minus 3, so I need to take that, square it, and add, I'm sorry, I think I said add 3 to it. I meant add 5 to it. Okay, so that's how I would do those. So on the next slide, pause the video for a minute and write these down. And then we're going to look at forming compositions. As you're writing them down or copying them down, think about which one is a bijection, which one's one-to-one but not onto, and which one's onto but not one-to-one. Okay, so now that you've got them all copied down, I hope you see that G is the bijection, F is onto but not one-to-one, and H is one-to-one but not onto. So when I go to do a composition, G or F of G, okay, that means I start at F and then M maps to triangle. Okay, so then I take triangle and I'm sorry, I need to start with G. I'm doing this wrong. Start with G. So the domain of G is 1, 2, 3. So then when I map 1 maps to N, then I take that answer and I put it into F. Okay? 1 maps to N maps to triangle. Okay, so that means that in the composition, 1, it's kind of like skipping the middleman. Right? 1 goes to N goes to triangle. So I just skip over that step and say, okay, 1 goes right to triangle. Okay, try to decide what, well, I'll do 2 with you. 2 goes to M also goes to triangle. Which I don't need to write it again. I'll just make my arrow go here. And then 3 goes to P goes to star. Okay, so for this to work, I had to have the range of G be the domain of F, right? Otherwise, this composition wouldn't work. So if you look at the next example, F of G, that's how I realized I was doing it wrong. Starting with F, when you have M, N, and P, M goes to triangle, and then I try to put that into G. Triangle is not part of the domain of G. Okay, so some of these are not possible. All right, so this one won't work. Not possible. There's one more in this row that is not possible. So let's do one more together, and then I will leave the ones for you at the end. Let's do this one together. So let's start with H. Okay, so H is triangle, and then I'm going to put that into G. So triangle goes to 1, 1 goes to N. So triangle goes directly to N. Star goes to 3, and 3 goes to P. Okay. And that's it. Nothing maps to M in this case. So that's okay. This is still a function. It's just not onto. All right. So you try the next 2 and pause the video, try those, and then I'll fill in the answers. Okay, so for this one, M goes to triangle, triangle goes to 1. N goes to triangle, triangle goes to 1. P goes to star, star goes to 3. Okay, and then this one's not possible. All right, so one more example, and then we will call it a day. So in this example, I just showed the function in a different form. I showed it with an arrow diagram like this. And if you prefer to, if you'd rather rewrite this function, where here's the domain. So this is a function that's mapping from, if I were to consider range and domain, It's mapping from the set 1, 2, 3, 4 to the set 1, 2, 3, 4. Okay, so that's what we're mapping here. So if you would prefer to, you could draw the arrow diagram so that it looks similar to the example that we just did. 1, 2, 3, 4. So 1 maps to 4. Oh, sorry. Gosh. 2 maps to 1. 3 maps to 2. And 4 maps to 3. So that's my function f. It is a bijection. And you're being asked to find f of f, which that might sound weird, right? But f of f, watch how this works. So we're going to compose the function with itself. So 1 maps to 4. Then we put 4 back into the function. 4 maps to 3. Therefore, 1 maps to 3. Okay. 2 maps to 1. Put 1 back in the function. 1 maps to 4. So 2 maps to 4. So try finishing it. Okay, 3 maps to 2. Put 2 back in the function. 2 maps to 1. 4 maps to 3. Put 3 back into the function, and 3 maps to 2. And so that would be the composition. So let's call it a day. Thanks for watching.